Hi, hello everyone. I'm Hamadouche from Heriot-Watt University. And in this presentation, I will introduce a mathematical framework for neural network compression in general, with a particular focus on large language models. The framework was motivated by a classical control theory, where if we have a state space description of linear system, two fundamental questions may arise. Is the question of controllability, which asks which inputs can drive state directions, and the question of observability, which seeks about state directions that can be inferred from the output. The answer to this was answered by Kalman in his paper, where he introduced a linear transformation that subdivides divides the state space into four fundamental subspaces, depending on controllability and observability. And he also proved that the subspace that includes controllable and observable states can describe the system, the original system, in a reduced model space, reduced model order. And he called it minimal realization. So in our work, it's an ongoing work. We're seeking to extend and generalize this concept to neural networks. If we analyze neural network or describe a neural network in state space, we can choose the information evolution direction. Either the information evolves in the depth layer index, or from layer to layer evolution, or from token to token evolution in generative AI, such as large language models. And for this is a description across network depth. A feed-forward neural network can be interpreted as a discrete nonlinear dynamical system. The hidden representation is the state at layer L, which is H sub L. And the next state is obtained by applying the layer transformation. And the term U sub L represents an external influence on the layer state, either from feedback or from feed forward or from external context. Depending on the model, this may be the original input or some perturbation. The matrix A sub L describes how an existing perturbation in the hidden representation propagates to the next layer. Of course, after discretization and linearization around a nominal trajectory, A sub L is the Jacobian that describes the propagation of hidden perturbations or hidden information towards the next layer, and B sub L measures how data excites hidden directions. We can further define a state transition matrix from layer K to layer L, which is a matrix product of the Jacobians. And the perturbation, the control enters towards layer K through local Jacobian B sub K multiplied by the transition matrix. Summing all over earlier layers gives the total perturbation at hidden layer H sub L. We can further define the controllability gradient, which is which defines the which is equivalent to the linear state description. The controllability gramian, the rank of the controllability gramian defines the controllability of the system. Large energy directions in the eigenspace of the gramian are hidden directions at layer L that can be strongly excited by the data. And this is local to the hidden layer. Likewise, by duality, we can define observability. If we take the output Jacobian with respect to hidden layer L. The hidden direction is observable if the turbine changes logits or probabilities or task scores, depending on the application. Of course, exact Jacobians, computation is not scalable, can be expensive to obtain, linearize around each hidden layer. And for this, we use a proxy, which we call evidence controllability. And we can show that this proxy approximates the controllability gramian under some assumptions about the perturbations. The observability gramian can be computed using gradients of the output with respect to hidden layers. Having obtained both gramians, we define a controllability observability score for each layer and for each entry. The weak risk score, R sub j, it's a metric that measures those directions that are highly observable, but very uncontrollable. Once we define the ranks, based on controllability and observability ranks of each layer, then the compression rule is to keep the top controllable and observable directions at each layer. So we call it CO, controllable observable, is a reduced architecture selection rule. And the reduced model should be fine-tuned after reduction or retrained from scratch or distilled. We apply it to a convolutional neural network on MNIST data with a depth of 5 hidden layers. And the CO approach selects a reduced channel realization, and we achieved 70% few parameters, a near teacher accuracy after fine-tuning. This diagram shows the original convolutional neural network and how the CO compression rule reduces each convolutional hidden layer to a reduced dimensional space. Now, we apply the proposed method to large language models, which is more challenging, still ongoing work. If we look at the autoregressive generation in language models, it evolves over tokens as well as over layers. So the next token is dynamically and stochastically determined by previous tokens, as well as outside extraneous context. If we define the causal memory, cache, M sub t, which incorporates all the keys and values from previous tokens, as well as from all layers, we vectorize it, and we treat it at the state of this dynamic system. It's a coupled dynamical system. The next memory evolves as a nonlinear dynamical system, function of previous memory, some context, and some parameters. The previous context controls memory, and memory determines future token probabilities. Attention is the mechanism that makes token time controllability meaningful. A token step T, the query vector Q sub T reads from cached keys and values. The values determine what information is injected into the current residual stream, and the keys determine where the model reads from by changing the attention weights. Linearizing around a nominal trajectory, assuming small perturbations. Same Jacobians reappear here, but with a different dynamical system. V sub T measures evidence control from the input, and C sub T measures the next token observability, visibility from the hidden, from the internal state space description. Likewise, we define controllability and also observability. We define again evidence controllability, which is a measure of the excitement of hidden layer when there is evidence compared to the excitement when there is no evidence or contradictory input evidence. Here this slide shows how we derive the evidence controllability from Taylor expansion. Here we define the controllability observability score, as well as the weak grounding risk, which detects highly observable but less controllable directions. The controllability observability is purely empirical. It's not a universal global certificate. It's an empirical task distribution measure depending on the data as well as on the locality. We applied it to open source language models, including Distill GPT-2, and Pythia 70M. The task is factual question answering and the 3 prompt conditions. We provide correct evidence, no evidence at all, and contradictory evidence. And for every model, layer, and answer token position, hidden states are compared across these conditions. The difference between excitement when there is evidence and excitement when there is no evidence measures how strongly evidence moves the residual state. This is just for diagnostic, not for compression. The next experiment will show how this can be applied for compression. The gradient of the target token log probability measures how visible that residual state is to the output. The 3 runs completed successfully. The GPT-like models both have hidden dimension or transformer width, residual width of 768, and Pythia 70M has a width of 512. Here we are profiling the hidden dimension, the observations that we show here correspond to answer token positions evaluated across factual QA cases. All models produce the required hidden states, gradients, controllability, observability scores, and weak risk diagnostics. The mean gold token probability on the rightmost column, is the average probability that the model assigns to the correct target token across all evaluated cases and answer token positions. Under correct evidence, like France's capital city is Paris, and the like, the probability lies around 0.43 to 0.47 across all models, indicating that the examples are not trivial completions, but are still responsive to evidence. Without evidence, as you can see in the bar charts, this degrades to around 0.2 to 0.3. The first empirical result is that all three models assign the highest gold token probability under correct evidence, and the probability decreases under contradictory evidence and is lower under the no evidence condition. The evidence lift, it's the difference between the excitement when there is evidence and when there is none. The leftmost column measures how much the gold token probability increases when evidence is added compared with no evidence. And the second column measures the margin between correct and contradictory evidence. Here we also inspect the,
That's showing that if you give the wrong, you give the wrong information, so there's no accurately given information. As in, when I unpack the bar chart, it's higher than the
yes,
section.
Yeah, okay. At least for these models.
Is that expected?
We didn't expect that.
Seems kind of counterintuitive, right?
Yeah, it seems. In the third scenario, when we give France's capital city is Lyon, we got high probability of than without evidence at all.
Yeah. Are these models instruction findings or your?
No, they are open source from Hugging Face.
But is there are they purely pre-trained on data, or is there an instruction function?
Pre-trained.
Oh, just pre-trained.
Yeah. We just provide the data for calibration and evaluation. Yeah, contradictory evidence remains above the no evidence baseline in these runs, suggesting that it is not a pure negative control. It still likely contains some maybe semantically related information that partially activates the correct factual region. Here we inspect these scores across layers to each model. Some layers are more excited than others. Yeah, also for token generation, the first answer token is apparently the hardest and most informative factual decision. It has the lowest probability. And it's much lower than later answer tokens, especially when no evidence is provided. Once the model starts generating the correct answer, later tokens often become easier continuations, as you can see by the increasing probability. Yeah, here we apply kind of some basic compression rule where we select at each hidden layer, we select the highly controllable, observable directions. And you can see that CO produces meaningful separation as depicted below. Selected dimensions are more controllable. And it gives a positive ratio between the selected ratio between selected and unselected dimensions. So as our findings support the token axis view of generation as a controlled dynamical process. Correct evidence consistently increases gold token probability, and CO selected dimensions concentrate evidence control and output sensitivity. The next experiment shows another tiny GPT model where we applied this CO rule for compression. We obtained 74% parameter reduction of a tiny GPT, 8 layers depth with 8 multi-heads transforms. And the evaluation loss is nearly identical. The validation loss is nearly identical to the original. This diagram shows how the CO process reduces the dimension of each multi-head transformer. Of course, different modules, they have different hidden dimensions, but we had to choose a uniform dimension across all models. Otherwise, we need to do some engineering to correct for inconsistencies. So based on the information and findings presented, we can claim that across at least these 3 models, prompt evidence actually controls hidden residual directions that are later observed through next token probabilities. And for compression, we can say that controllability, empirical controllability observability framework identifies residual directions that are useful and grounded enough to preserve, while weak risk identifies output visible directions that may require monitoring. Of course, this can be used, for example, as an extension to detect hallucination, highly observable directions, but less controllable, which suggests some memory or some risk. As a conclusion, CO framework identifies substantially smaller model, about 71% fewer parameters for convolutional neural networks, and 74% fewer parameters for the tiny GPT model. The common interpretation is that empirical controllability and observability define a compact, deployable architecture. Output Jacobians reveal which hidden layers, hidden modes and directions are visible through next token probabilities for the generative AI. And across the tested models, correct evidence increased gold token probability relative to no evidence and contradictory evidence. CO selected dimensions concentrate evidence controllability, output observability, and auditable score. And that's it for my talk. I'm happy to take any questions if you have. And feel free to suggest any extensions. It's still ongoing.